Now we will see about the third case, which is cylinder insulated from outside surface. So be very attentive because it is quite difficult topic to understand at first go. But if you read it a number of times, you will understand it very deeply. It is not that much difficult. For first time it will appear difficult. So let's say this is a pipe and we want to reduce the heat loss, and its radius is R1 and outside is some fluid, because that convection is occurring at TA infinity and H is heat transfer coefficient. So Q without insulation, we know without insulation Ts minus T infinity divided by 1 by H 2 pi R1L, right? To reduce the heat loss, we are insulating it, let's say. So let's draw its cross-sectional view. And this is the base material. Consider this outer surface of this base material as R1 radius. Okay, of course this is also the radius, but we are not concerned about the concept of thermal resistance of the base material, and we are insulating it from outside, right? This is the insulating material we are putting, right? This is thermoconductivity of the base. So what will be the radius of this insulating material we are putting on outside surface? We have to find that H0 to infinity, right? After insulation it will look like this. You have to find this R value, okay, at some general radius. So first of all, see what is happening here. Let's write total resistance. First there will be a conduction in insulation, right? Let's write ln R by R1 divided by 2 pi K insulation L plus 1 by H times 2 pi R1, sorry, it is R, not R1, it is the outside surface, no, outside surface from here. From here it is transferring, so it is R times L. So we can see here that if we increase the radius of insulation, means if we increase the thickness of insulation, if we increase, then ln R by R1 will increase. What will happen to the convection resistance? It is in denominator, right? And 1 by H times 2 pi r RL, right? It will decrease. So we don't know that total resistance will increase or decrease. So this is the problem. So we have to find that total resistance will increase or decrease. Okay, so we don't know about that, and because of that heat loss may also increase or decrease. Okay, this happens when we are insulating the cylinder and sphere from outside surface. Okay, so to find that at what value the resistance is minimum or what, let's differentiate this total resistance with respect to R, right? We don't know the resistance will be maximum or minimum, so differentiate this total resistance with respect to R. You will get like 1 by 2 pi K insulation times R times L minus 1 by 2 pi R square H naught L, and putting it as 0. So for maxima or minima we will get the critical resistance, critical radius of the insulation as K insulation by H naught. So critical radius is depending on the insulating material property as well as the convection coefficient. So total resistance is minimum or maximum at this radius, we don't know. So to find that, we can again differentiate that as we know from our school level mathematics. So if it is positive, then it means that at RC total resistance is minimum. If it is negative, it means that at critical radius the total resistance is maximum. Okay, if you put if you differentiate twice, again you will get like 1 by 2 pi K insulation R square L, of course with minus sign, and plus 1 by 2 pi H naught L 2 pi R cube, minus minus plus. Okay, because one more minus will come because of the differentiation of this. Its differentiation will be minus 2 pi R cube, right? Because of that this minus will become plus. Okay, so if you put the R as RC here in this equation, if you put, you will get H naught square divided by 2 pi K L K insulation cube, which is greater than 0 because all are positive numbers. So it means that total resistance is minimum. Total resistance is minimum at critical radius of insulation. It means when total resistance is minimum, what will happen to the heat transfer? Delta T by R total heat transfer will be maximum at RC. Okay, similarly for sphere we can derive, for sphere again start from total resistance, one by 4 pi K insulation times 1 by R1 minus 1 by R. So same figure here. We are suppose that we are insulating the sphere from outside, so it is R1 and this is R, and for first the thermal resistance will come from the conduction resistance of the insulating material, which is nothing by 1 by 4 pi K R1 to R. So 1 by 4 pi K insulation, 1 by R1 minus R. Then convection resistance 1 by H on the outer side times 4 pi R square on the outer surface, this surface, right, for sphere. Again, if you differentiate, and put to 0, you will get critical radius as 2 times K insulation by H naught. Okay, this is the critical radius of insulation. If you want to find the critical thickness, how will you find? Critical thickness will be this, R minus R1. R, what is R? RC minus R1. Okay. So some of the conclusion we can make from here, that in case of electric wire, the purpose of the electric wire is to provide safety from electric shock, as well as to increase the heat loss from the wire surface. Okay, in case of electric wire, we need that when we are insulating it, the heat transfer should increase. Okay, and in case of steam pipe, the purpose of the insulation is to reduce the heat loss. Therefore, when we are insulating it, so after insulation, heat loss must decrease. So RC, that is the critical radius, is the radius at which total resistance is minimum. It means heat transfer is maximum, as we have seen. So for electric wire with insulation, so different application have different requirements from the insulation. So in case of electric wire, we need that when we are insulating it, the heat transfer must increase to dissipate the Joule's heating which is produced inside the wire, right? Otherwise, the copper inside the wire may melt or will hinder the application of that wire. So Q with insulation must be more than without insulation. And in case of steam pipe, we need the heat transfer with insulation less than the heat transfer without insulation. So heat transfer must decrease when we are increasing the insulation. So from now on, we will take on to the next lecture. Thank you.